Right, let's look at how type checking works with polymorphic types. And first, let's remind ourselves what polymorphic types are and what they mean. So polymorphic type is one that may contain type variables. And so we can see some examples here. And a type can contain just one variable, it could contain the same variable more than once, or it could contain different variables. We see examples of all those in the examples listed here. Now let's have a look at what a polymorphic type actually means. A polymorphic type with variables in it stands for all the types you get when you substitute type. When you replace the variable, you substitute the variable with just a type. So for example, if we have the type list of A to list of int arrow B, so instances if we substitute for those types, we might get int to list of int to list of int to bool, where we've substituted int for A and bool for B. We get the same thing, list of int to list of int to int, by substituting int for both A and B. And in the final case, I just wanted to show that the types, we can still get a polymorphic type, but it's just more specific. It's list of C to list of int to C to A, because here for A we've substituted list of C, and for B we've substituted function from C to A. So that general type, list of A to list of int to B, stands for all the things that are more specific, all the things you can get by replacing something general, a variable, by something more specific. That's a type or a type expression. So that's what we have in terms of meaning here. A polymorphic type stands for all those different things. So you can see that this makes type checking a bit more complicated. If you apply a function that has a polymorphic type to an argument, you don't expect the argument to be exactly that type. It might be an instance of that type. That will be fine. It will still type check. So let's look at some examples which take us towards that. Now here's an example of a function definition. F takes a pair of things x and y and returns a pair with x at the front and a list now which is from the character A up to y. So what that tells us is tells us nothing about the type of x. So x will have type A, where A is a type variable, but it tells us that y must be a character. Because why is that? Because it's used in specifying the range of values from character A up to y. So y itself must be a character. So this tells us that F takes a pair of things of type A and char, and it returns a pair of things of type A and list of char. So we've got a type, that's the type of our function F. Now what about a function G that takes a pair of things and returns the sum of the value on the left and the length of z's? So what can we deduce from this? Well, length returns an int. So if the thing on the right of the plus is an int, the thing on the left will need to be an int. So that means that m, the first half of the argument, must be an int. What does it tell us about the z's, the second half of the argument? It tells us it must be a list of some kind, but we don't know what type. So let's just say list of B. So now this tells us we provide as input an integer and a list of B, and what we get out is an integer. Okay, so we've got our two functions, f and g. F is of type pair of A and char to a pair of A and list of char. G is a function that goes from int, a pair int and list of B, to int. And what happens if we compose the two together? Well, we require that the output type of f is the same as the input type of g. Just as it's a similar constraint to the constraint we get when we type check an application. So what we need here is that the input type of g, which is the value, the pair int and list of b, needs to be the same as the output type of f, which is a to list of char. So what we need to do now, those two are not equal. As you can see, we've got a paired with list of char and we've got int paired with list of b. What we have to look for is what we call the unification of the two, the most general thing that is an instance of both of them. And here we get that by replacing a with int and b with char. So if we do that to the functions f and g, we see that we want to think of f as being from int, a pair of int and char, to int and list of char, and we want g to go from a pair of int and list and char to int. So when we do this application, or when we build a function composition, we have to use this process of unification, finding a common instance of those two, solving that so that we can see that we're able to form this function composition. And so we can conclude that h is of type int comma char to int by composing first f then g, we get this function h of that type. Now let me talk a bit more technically, a bit more formally about unification in the next section. But the crucial thing here is to see that we need to find a way of making the types of the function argument and expected value, or the types of the input and output in a composition, the same. And that's what this process of unification does.